在进行漏洞研究的时候，那最怕的就是遇到要分析的 binary 没有 symbol。那这时如果目标再加上混淆的话，那相信这个研究没有个 N 百天的逆向工程是没有办法开始的。所以接下来的讲者就是要跟我们分享如何去减少这些痛苦。那让我们跟着讲者一起来看看他如何在没有 symbol 的状态下去分析经过混淆的 Windows driver， 并且成功找到许多漏洞的故事吧。那让我们掌声欢迎 Philip。
Thank you, everyone. Hi. So yeah, today I'm going to talk about what the hell is Windows Clip Service. And so, hi, I'm Philippe Lorette. I'm a senior vuln researcher at Cisco Talos, and I focus mostly on Windows these days. So basically, we look for vulnerabilities. I look for vulnerabilities in like drivers or like Windows applications, and then we report that to vendors. We disclose like advisories on our blog, and we create detection rules and so on for our customers. But yeah, and so like these days, my focus is on Windows. So what can you expect from this talk? It's roughly like a 40-minute talk where I'm going to talk about Clip Service and specifically clipsp.sys, which is the driver that implements, which implements the functionality of the Clip Service. And it's largely like an undocumented driver. And so I'm going to dwell quite a bit on the reversing process. And I also found multiple vulnerabilities in the code, and so I'm going to share a few. And I think the most interesting takeaway from this talk should be like, the process for reverse engineering this type of target and understanding the kind of attack surface that this driver represents. And so yeah, don't forget like hack the planet. So yeah, what is clipsp? So clip stands for like client license platform. SP is like system policy, which I think is some kind of like various configuration settings and features and so on Windows. And there is a bunch of components involved. So clipc.dll, which is like the client side used by other like Windows components to interface with the clip framework. Clipservices.dll, which is an RPC backend that clipc talk with, and the clipsp driver that's kind of implemented these features. And I know there's like a lot of clip in that, but has nothing to do with this guy that we miss dearly. So yeah, past work, other people have worked a little on that. Mostly for clipsp, there is this one GitHub page. If you guys want to take a picture of that, it's fine. So that GitHub has a lot of information. I use that partially for my work, but some of the limitation of that GitHub is that there is no documentation, and it's kind of, half broken code, so you have to connect the dots to make it work. We're going to talk about Warbird at some point, and so there's a bunch of resources over there. And CVE-wise, I found two CVEs that affects clip service. But from my experience with disclosing to Microsoft, it's likely that there might have been other vulnerabilities that were not labeled as clip vulnerabilities, or just Windows kernel vulns. So there might be more. Okay. So why do we want to look at driver in general and clipsp in particular? So I was looking for EOP in Windows drivers, like elevation of privilege, notably because it's easier than like remote code execution, and Microsoft has like a bug bounty program. It's interesting, and apparently like threat actors tend to leverage way more like EOPs than just like RCs. So that's pretty relevant to research those. And from a curiosity standpoint, I was looking at a bunch of drivers to pick my next target, and I imported clipsp in IDA, and it looks like that. So usually, like when you look at Windows drivers, you're going to have like symbols and stuff, but in that case, no symbols. It's like, what are they trying to hide? So it's getting my curiosity like startled. And then, I started looking at the functions. Yeah, you can see that. So there's like a bunch of stuff, but we can see like the second red box that says location, whatever. So IDA is not even able to look at the function correctly. And if we click on that, it looks like that. So that's crap, that's not good. And I was like, oh no, that is obfuscated. So I was pretty sad. And I was like, okay, we need to get working on that. So how do we deobfuscate that driver? Just to give a TLDR, like it's obfuscated with Warbird, which is like a proprietary obfuscator from Microsoft. It can do like a bunch of different obfuscation. notably data structures, self-modifying code in the kernel. So that's pretty shady, and that's kind of why I found clip-sp in the first place. Self-modifying code in the kernel is no bueno. And you can also do syscalls to decrypt and re-encrypt section or execute payload. I won't be talking about that one today, but still pretty cool. So that's the screenshot of the previous slide. If we rename the things a little, that looks like that. So there is like two decrypt function here and there, and then like an encrypt function, or like throughout the talk I may say decrypt, I may say deobfuscate. It's the same thing in that case. And then you actually have the function you want to execute. And so if we click on some of those decrypt functions, we're going to see stuff that remap section to become like writable and then like self-modifying. And we're going to have like that type of awful stuff. So like, yuck, I don't want to deal with that, but that's what we have to look at. So how to deal with this kind of binary obfuscation? Usually the trick is to dump the driver, like, like if you deal with Packer, for instance, you just load the thing, let it deobfuscate itself, and dump it. But in that case, it's not going to work because, as we saw in the previous slide, it's going to execute a function and then re-obfuscate itself. We could re-implement the algorithm, but that was like pretty tedious. There's a bunch of, there's like multiple functions. It's complicated. But we'll see that later on. And another approach that I think is more interesting, which is lazy and smart, depending on if you're optimistic or pessimistic, is to try to leverage existing code. Usually, you could try to like import the DLL and just execute the function yourselves. In that case, because it's a driver, probably more complicated. There's a bunch of kernel API, so that's tedious. But option 2, you could emulate the code. Usually, I've done that with Unicorn in the past, which is really nice. But it's like still like a bit of work. But it turns out like actually someone did option 2, so that was the GitHub I was sharing before. And to give an idea of the process they followed was import the driver using quilling, and quilling does the heavy lifting of loading the driver, loading all the dependencies. And that's nice, but it's kind of slow to run because it loads everything. And if you have your Python script and you make a mistake, it takes like hours to like redo. But it's less effort than doing everything by hand with Unicorn. And that person had no documentation on that script, so I'm not exactly sure what was the intent, but I think the point was executing a like initialization function and then dumping everything that gets like modified, which is not exactly what I wanted to do, so I went on and to improve the script. So if we look at the stuff we had before, the decryption function, the execution of that function that we want to like look at, the idea is we could cross-references all the call to this decrypt function, backtrack to recover like the arguments that kind of like specify, what to decrypt, how to decrypt it, etc. List all the calls to decrypt, not only for this function, but throughout the whole binary, and then use quilling to execute all of those functions, and then dump the memory range and re-import that in IDA. So that's kind of what it looks like in IDA Python. You get the crossref using that API from IDA. Then you can use that function that's on the next slide to backtrack the registers, and then you save that and keep track of like unique entries, like specific combination of arguments. To retrieve the registers, it's pretty easy. So like if we look on the disassembly on the right, we can see that it's just putting addresses in RCX and RDX. And so we can just walk back, the instruction using prevhead, which is like a Windows IDA API, and then retrieve the values that are being put there and log those. And then you can list all the calls, and I print them here. It's pretty easy, and then you can copy paste that, put it in your quilling script, and so then it works. So like the stuff I copy pasted are here. And here you have the decrypt function. So I had to hardcode the addresses from like the beginning of the decrypt function and the end of the decrypt function. But that's just from like looking in IDA. And also it turns out there's two decrypt functions that behave exactly the same. So there's the second one. And yeah, here's like what we copy pasted from IDA output. And then yeah, we can dump the whole memory range, save it to a file, And then in IDA again, we can just load that file, patch the bytes, and suddenly, instead of having something like that that looks like all junk, we end up with something like that, which is much nicer, which is like the actual like function is deobfuscated, and actually the whole binary is deobfuscated. So the deobfuscation is complete. We're pretty happy about it. Okay, so we were like able to deobfuscate the stuff, so now we can actually start doing the real work, which is reversing it. The plan for that usually is we want to understand how Windows communicates with the driver, because that's how we're going to communicate with it, and it's also like the attack surface that's being exposed by the driver. But in parallel of that, we also want to reverse the stuff, understand the data structure, the logic, etc. And in the meantime, trying to keep an eye for potential vulnerabilities, because that's the end goal, looking for vulns. So how do we talk with the driver? Usually, like what you expect is like a device driver is going to create like a device, like IOCTL handler, or some form of handlers. But in that case, nope, none of that. And instead, we have the clip sp initialize function that we were looking at just before, that actually takes like as an argument like an array of, that means populates an array of function pointers. And if we grep for that symbol like throughout the file system, we can find that NTOS kernel and a few other drivers like call that function and use it. So that's what it looks like inside NTOS kernel. We can see it's like calling the function. And inside the driver itself, that's how it looks like. It populates all these function pointers. None of the names were there originally because, as I said, we don't have symbols, so all the names comes from reversing. And here, like a kind of like a trick is the best way to deal with that is to create a structure with like, I don't know, like 51 entries, because like 51 functions, and like rename them and define them. And this way we can easily cross-ref stuff afterwards, like both in clip-sp but also in NTOS kernel, which is pretty useful. And so that was on the kernel side, but like user land, how do we deal with talking with the driver? So, I mean, still in the kernel. We can cross-ref into NTOS kernel how those functions are like used. And so basically we land into this exp query system information function, and this like crazy call stack. But really, like the whole point is you call anti-query system information with a system policy information class, which is undocumented, to reach those functions. And the idea is like there's like a whole like shebang of structure, but you have a command ID. I'm not sure that's a real name, but that's the ID. That's basically specify inside that system policy information class which function you want to call, which operation you're trying to do. And that's changed the look of the payload. And unfortunately, this payload is also obfuscated, so we have more stuff to deal with. So now I'm going to look at the diagram of the payload. I wanted to try something new. I did like some handwriting. Hopefully you can read what I wrote. That was cool. It's bright, sorry. So you have the inner payload as like size, so it's a 4, and then you have the command ID, so it's a D word. Then you have XA0 blob of data, and this like warbird stuff. And then like 8 bytes, like warbird key, 8 bytes a queue, like a timestamp, and then whatever data that's relevant for the command you want to execute. This whole stuff then gets packed into this structure with like you have like the number of entries, it's like those, the size, the payload, and also timestamp. I suspect all those timestamps is just to have variability in your payload. And then the whole stuff gets encrypted again using a different flavor of warbird. And then you have more warbird stuff here. And basically the difference is, so this one, which is like the auto payload, is basically going to tell the kernel how to decrypt the data you've provided. And meanwhile, this side here is going to tell the kernel when it sends you a reply, how to encrypt it so that, or obfuscate it, so that everything is super secure. Not really, but so yeah, we have more warbird to deal with, as I said. And funnily, I asked ChatGPT to draw me like a warbird, and that's what it came up with, which I think is pretty funny. But yeah, so that's really what it looks like, less cute than the rainbow bird. But this time we kind of have to deal with it. We cannot just quilling our way out. So what it is, it's basically called like Feistel rounds or Feistel cipher. And so basically the idea here is that you have basically you split your data into chunks, And one side gets unmodified and the other gets fed into the facetel function that's also keyed, and you XOR the two, and then you swap them, and you keep doing that with multiple facetel rounds, and eventually you end up with a ciphertext. And the beauty of it is that to decipher it, you do the same operation in reverse. So the facetel function themselves don't have to be invertible. And so yeah, I was talking about warbird regs, warbird key. So what I do, so as I said, facetel cipher. So the first blob, like the XA0 sized buffer, is basically a list of operations. So like the kernel will use that information to call specific function with specific parameters are provided there, and that's basically the instruction set for the kernel to know which operation to perform to decrypt the blob that you send. The IBate key is just a key. And as I said, the warbird material in the inner payload is to tell how to encrypt the reply, while the warbird material in the outer payload is to use to decrypt the stuff. And how you find this algorithm and all this key material, what I did was find like a binary that actually interacts with this API and basically look at it in X-ray and repeat out. So we can creep for like grep, sorry, for a bunch of symbols, strings until we find something interesting. This function here is an example of something that interacts directly with clipsp. And so we can open that in IDA, X-ray, copy paste the whole stuff in Visual Studio and basically have the blueprint to deal with that. Oh yeah, and important, you need to keep the same key material as the algorithm you're using because those are paired. And unfortunately, I'm not sure if I can share like this code, but the GitHub repo I was mentioning, there's also some broken code that deal with that. And if you try to implement it yourself, you can also reach out to me, and I can happy to help. It's just I don't want to get on Microsoft's bad side by sharing too much. So yeah, to communicate with the driver as a TLDR, you use anti-query system information with the system police information class. You have a bunch of nested payloads with like length data. One of them is like the command ID that specifies the rest of the data you're going to use, and then a bunch of warbirds to do encryptions. Okay, so we figured out how to talk with the driver. So what does clipsp does? And that's a good question. Unfortunately, don't have time to like reverse the whole stuff or like, to present the whole stuff. But basically, you have the system policy that it takes its name from. For instance, anti-query license value is one of the functions that call into clipsp. And there's like those keys that kind of specify, like for instance, if your Windows is genuine, if you have like some features enabled, etc. For instance, Notepad does call into clipsp with that, so it's kind of surprising to see all of this warbird crap in Notepad, but it's scope creep or something. It does also EFS, which is encrypted file system. So it deals with key, headers, etc. And in that specific case, you also find clipsp in file system drivers. So I think like NTFS driver and maybe XFAT or something will also call sp initialize and load EFS functions and deal with those. And it also does like device attestation, which I think is really interesting. So the first time you connect your machine to the internet, I'm assuming it reaches out to Microsoft, and there's going to be some kind of like key exchange or like material exchange. And basically your device receives like a device ID and I think generates some key material that can get kind of like signed by Microsoft. And so this way, Microsoft can identify your own device and you can do stuff like hardware binding for licenses and also like HMAC and signature to do like device authentication and that type of stuff. And finally, Windows application licenses. So like if you download stuff from the App Store, all of them have licenses. And for instance, like, is your stuff expired? Is it leased? What type of license is that? Sometimes, you want to encrypt your application, so it also contains that kind of stuff. So that's the idea. And yeah, how can you find all of this info, all of these symbols, etc.? As I said, NTOS has clipsp has no symbols, but other binaries might. So a good trick is to like start graping the whole file system for like all of those like warbird stuff, so you can find other binaries that are calling into the thing that may have symbols. Like all the clip stuff have the symbols stripped, but other drivers may not. So that's useful to retrieve like function names and so on. And another cool trick is clipsp likes to log stuff using ETW write transfer. And it contains a lot of information like function names and variables, which is pretty neat. So here's an example here of that's a screenshot from one of the functions in clipsp. And so you can see here, that's not obvious, but it points to a blob of data that we're going to have on the next slide that defines what wants to be logged. And here you have the number of entries you're logging, in this case 11, and all of those are event data descriptors, as it's written here. And IDA knows that format, so you can define that variable, the v30, as such, and it creates that structure, and you have all the pointers there for those variables. And for these names that I commented here, which are variable names, they come from that slide, which is the blob I was describing. And so here you have all the variable names, and here you have the function name. So just thanks to all the logging clipsp does, even if the symbols are gone, it tells you a bunch of information already, which is actually pretty useful to understand quickly what certain stuff does. And as a bonus slide, if you want to look at these logs, you can use this tool, trace event. On GitHub, it's using, I think, maybe undocumented API, I'm not sure. But if you use these two commands, you can basically start printing in the shell all the events are being logged. And this GUID here comes from when clipsp register its event register thing, by calling this function. So that's specific to clipsp. Okay. So after a while, we can keep reverse engineering and stuff, and we end up with this stuff, which is that's my interpretation of all the functions that are being exported by clipsp, and pretty much the attack surface that we can somehow reach when we look at this driver. And further, I mentioned before this command ID, which is all the potential stuff that we can reach through the anti-query system information with this whatever the system policy class. And these are all the command ID that exist. Some I'm not sure what they were. Some are the actual function name, thanks to anti-OS kernel symbols. But there's a bunch. So that's the whole attack surface. And I kind of narrowed down. I looked at most of that, but the interesting one are these two. Mostly the update license, which is used for installing licenses for your apps mostly, and a few other stuff. So we want that function install licenses, what a license looks like. Or first, what does it do? Those licenses can be used first for the device, the identity thing I was talking about with the cryptography material, the device ID, and so on. But most of them are used for the app store for installing your app and the license that goes with it. So key material is hardware binding. So if you, I don't know, run Minecraft from the App Store, you're going to have a license for Minecraft, in your stuff. And they might be automatically installed behind the scenes. So if a license is expired and you connect it to the internet, it's automatically going to try to fetch a new one. And if it can't, it might fail. Which is funny because if you Google clip stuff, you can find people complaining on the internet, Reddit and so on, about all these error messages they encounter because of clipsp breaking, especially invalid device ID. If people changed some hardware and the Minecraft doesn't start. And so how do you install that stuff? You install it with that sp update license, so it's command 100, and basically you have a series of tag length value. Once again, nothing is documented. But they also exist in XML mapping. So if you spend some time reversing stuff, you can also find function you can find names and so on. And then there is this internal map from the tags, from the taglet value into an internal index. So when you load the license inside clipsp, it's going to store the content as as an internal index. So some mapping. And unfortunately, those licenses are signed. So first, it specify the kind of license, and you have different signing authorities depending of what you're doing. So the device ID license is not going to be signed by the same authority as your Minecraft license. And you have built-in hard-coded public key in your driver. So to give an idea is like most of the types, like that's another like picture if you want, but types of licenses, no, like fields that are like in the license, and here is the conversion from like the internal type to like whatever tag that's actually being used by the license object. So there's a bunch of them, but really it's expiration date, crypto material, maybe some hardware binding, and that's pretty much it. Oh, and fun fact, those licenses are like stored in the registry at that location, but if you want to look at it, you need to be system. And so to do that, like as a normal user, you can run psexec with that flag to run regedit as system, and then you can look at those files. And there's like subkeys in that. The license data is basically the whole license, and then like more stuff, not like all confusing. But we're going to look at the license data mostly. Okay, so now it's time to really hack the planet and find some vulns. First one, like, okay, we need to parse a bunch of TLV data. What could go wrong, right? So that's the function that does the parsing. So it's smart enough to make sure, like, the values are not going to overflow and so on. And then it does some extra validation, but it's pretty much just like checking stuff out like within range. And then it converts the data from the tag we were like talking about into these internal indexes. So they go up to like 25. And just keep going, parsing the stuff. And so if you have like a type 24, it's going to break out of the loop and save the data in two locations, like the beginning of the data in that pointer here, and the pointer to like entry 24 in that pointer here, in that license object. But then it resumes the processing after that. And that's where like the signature, like type 24 is the signature of your license. And then it keeps doing its stuff. And to do a license check, down the processing line, it gets the data from what was saved before, like the pointer to the data, and then it's going to compute the length by doing the difference between, the position of the signature versus the beginning of the license. But I don't know if you're paying attention, but something interesting is here we have a signature bypass because, like the processing keeps going, and so we have two problems. We can append more data after the end of the signature, and it will be never checked, for like authenticity. And on top of that, if we look back at the stuff here, the way it works is like it takes an index and then save it in this array. So if you have multiple times the same tag, it's going to overwrite a previous entry in that buffer. So we can also overwrite legitimate entries of your license file by just adding more data at the end. So the consequences of that is that you can tamper with license content. You can change expiration dates, encryption key, hardware bindings. But you can also change the device ID of your machine, and that's of course increasing the attack surface because now we can send data that we shouldn't be able to tamper with. And just to give a funky example here, I changed the expiration date of the license of Notepad. So here I'm just opening Notepad. It works. It's all cool. But then, like with the proof of concept, I'm appending data to the license, the Notepad license, to just say it's expired. And when you try to execute it, it doesn't work anymore, and it's have this weird error message. To be fair, like in that situation, the VM was offline. If it was online, it would just fetch a new license. So, but that's just interesting to see like how much like scope script you have in your like Notepad. Second vulnerability that I found, the device ID stuff I was talking about, that was pretty interesting. So big blob of code again, but basically like when you're installing the license, it's going to like check a bunch of stuff, and it wants to check that your device ID is legit or something. And so here it fetch the size, allocate a buffer, and then get a pointer to the data, copy the data, normal stuff. But if we look at how it does that, so to get the device ID size, if there is an entry of type 5, it's just going to use the entry size from the original TLV buffer, and we'll just return that. But if there is no entry of type 5, it's going to check if there's an entry of type 18, and if so, it's going to dereference the first 2 bytes of the buffer that you had provided in that entry. And likewise, for getting the data of your device ID, it's just going to return, like, if it's a type 18, it's just going to return like whatever data comes after the first like word size. And so once again, like if you're paying attention, here we have an out-of-band read, because basically nothing checks if that size field that's being dereferenced is actually within bound of the license you've provided. And on top of that, it doesn't check either if the size that is supposedly legitimate match. So if you create a device ID field of size 0xFFFF, it's going to try to copy like 1,000 bytes, 10,000 bytes, out of the license you provided, and it never checks, if it's fine or not. But that's not the end of it, actually, in that specific case. So there's the same function we're looking at, but if we pay attention, what it does here, it's like get the ID size, which could be read out of bound, and it's used to allocate the buffer, and then it does a bunch of stuff, and then somehow it checks 1,000,000 times the size again, and it used a different value from there to do the memcopy. So really what we have here is a double fetch. Because it checks multiple times the size field, and that gets messy. So yeah, we can turn the out-of-band read into an out-of-band write in that device ID field, because it's checked twice, once for malloc and once for the memcopy. So it's a race condition, and the idea is basically like if you can time it right, you could swap the value that's read out of band as a size field between the allocation and the memcopy. And so you can lead to like heap overflow during the memcopy. The exploitation strategy for that is you create like a big license file with a bunch of junk data so that it's just like nicely like aligned. And then you make it so that your device ID field just is right at the end of your license, and so that the first 2 bytes of the device ID field will be like out of bound. And then you do some like fancy like heap feng shui so that you can control what happens right after your license. I kind of tried with these 2 functions, which give some results. And apparently the good edge case is like if the size you allocate has that property, so if the size modulo 10,000 is that, there would be like no headers, and so you're like a raw blob of data, so it's more convenient than other ways. And then you can spam creating and destroying these namespaces while you install your license. And so if you have bad luck, you get a blue screen of death because it reads out of bound like an unmapped page and crashes. Otherwise, nothing happens, and if you're lucky, you actually get like an out of bound write. I don't have like the full weaponized exploit, and instead I'm just going to showcase this like out of bound write. So the trick here is just like put a bunch of breakpoints, one just before the malloc and log the size, and then one just before the memcopy, and check if the values are different, and if so, like just print it in the console and be like, okay, we managed to get an out of bound write. That looks like that. I don't know if you can see my GDB. That actually runs for like forever. I think it takes like 10 minutes and crashes like every other time. So it's not the best exploit ever. So like it runs for a while, and eventually it keeps running, and you get that stuff where like I don't know if it's super easy to see, but it allocated like 14,000 bytes and tried to memcopy 58,000. So that's a sign that you had indeed like an out of bound write, and that's the book. After that, we had like more bugs that we reported from at Microsoft, but mostly they were like all the same vein of you're dereferencing fields in that structure that you shouldn't. all of those are like out of band reads, not good. So yeah, we reported all of that to Microsoft over 90 days ago. Most of like they were fixed in July. We have like a bunch of advisories on our blog, and that's the CVs that we got for those. As next steps, what can you do about that? So interestingly, those aren't just regular like EOP, but it's also like a sandbox escape, turns out, because anti-query system information is reachable from like a low privilege application container. And those LPAC are used for like browser isolation, parsers, and so on. So I wasn't aiming for that when I was starting my research, but Microsoft provided a tool to check if like your code can run in a sandbox, and it did, and it worked. So that's way more interesting in the eyes of Microsoft. And yeah, of course, we can tamper with license file, so you can change your device ID. I think there's interesting stuff to think about with the device authentication aspect of it. You can be malicious and expires, other licenses, etc. And then, like another like fun stuff that's good to think about is that the self-modifying code in the kernel is probably not the best thing in the world. Like when you think of all the protection that exists, nowadays, and here you could just like tamper with it and probably like execute some fun stuff, in your kernel. Now, like if you want to take this research further, like there is still like more interesting stuff to look at. The EFS, so the encrypted file system, like it touches some like file system drivers and so on. There's like many system policy objects that may or may not directly be handled by clipsp. And some of the flags I've seen in the kernel, like mentioned, like Azure integration. And so to me, it looks like some of the functions are like conditionally conditionally enabled, I think. So to me, it kind of says that I probably like keep developing the driver. So if you keep looking at it, maybe there will be like new stuff popping up that could be interesting. And even beyond clipsp, there's like more like stuff that like obfuscated by Warbird. Put like a bunch of names there. And to give another example of funky anti-query system information attack surface was that class system control flow transition, which is actually like executing Warbird on a heap. And there's like a CV recently about that. So all of those are like kind of interesting stuff that go beyond this talk. And yeah, so as a quick conclusion, I think to me what's really interesting is like how like the bugs I was presenting are like really simple, let's say, trivial, and nobody found them because the obfuscation makes it just really hard to find. And so I think it's both interesting from a vuln research perspective because you need to like invest a little more upfront, to get that running. But then like when you're beyond the hurdle of obfuscation, maybe way less people have looked at it, and like be like spicy stuff to look at. And then like EOPs are like the bread and butter of like all the threats, the threat actors. So like it's definitely interesting to look at those. And yeah, thank you. That's my rendition of Clip Warbird, ChatGPT. If you have questions or comments, you can reach out to me on Twitter. And yeah, just thank you everyone for your time, and thank you HitCon for having me. It's really happy. Thank you.
好，谢谢讲者精彩的演出。那现在还有2分钟，那会场有人有问题想要问讲者吗？哎，那边有人要问问题。哎，他前面桌子前面有麦克风可以问。
Hi, thank you for your awesome speech.
Thank you.
I have a question. The way to get to the position where the vulnerability exists is really complicated. How many time did you take for this research?
To get to the bug, I think it only took me like, I don't know, 2 months, I think, or 1 month. I feel like writing all the reports and stuff took way longer than like finding the stuff. But I think I got lucky because I was just like looking around and I was like, oh, that looks spicy. And then there's like a few more like hurdles that I didn't have time to talk about in the talk. But yeah, I think it was just a few months project.
Thank you.
好，那还有其他人有问题吗？好，最后30秒。好，那就让我们再掌声谢谢讲者。